Great, thanks. So welcome everybody to our, what is our third Dataset Award winner webinar. So I first want to congratulate our speakers today, Katarina and Bruce, for the Dataset Award, and Sumit. This has been, I think, a really successful incentive to curate good data sets for other people to use, and they've done a great job with theirs. I'm Scott Brandenburg at UCLA, and I'll be doing the introduction today because Charlie Day, who usually does these, is traveling. His name is listed there, so I still kept his name. This is his slide. And I also kept the screenshot. The DesignSafe website doesn't look exactly like this anymore. We've updated the cover picture, but this one is the Centrifuge, so it's really well suited for today's seminar. So just a few logistics before we get going. There will be a survey toward the end. We like to get feedback about these webinars so that we can improve the format, make it better to serve everybody well. You should have gotten a notice the webinar is being recorded. So this will get posted to our YouTube channel within a few weeks, and there will be a record of it if you wanted to come back and watch it or go and comment on how wonderful it was in the comments of the YouTube channel. Okay, I'll go ahead and introduce our speakers today. First, the Dataset Award winner presentation is titled Centrifuge Testing of Liquefaction-Induced Downdrag on Axially Loaded Piles. And our speaker will be Katarina Ziotopoulou, who received her degree in civil engineering from National Technical University of Athens in 2007 and master's and PhD degrees from UC Davis. I think we almost overlapped at UC Davis, but maybe not by about 4 or 5 years. I graduated from there long before she was there. She joined UC Davis as a faculty member in 2016, where she's currently an associate professor and focuses on numerical and experimental investigations of geosystems subject to liquefaction and cyclic softening and development of physics-informed data-driven approaches for geotechnical earthquake engineering. Bruce Cutter is also with us today. He's professor emeritus at UC Davis, has his bachelor's and master's in civil engineering from Davis, and then a master's and doctorate of philosophy from Cambridge University. And he returned to Davis in 1983 and was then the director and associate director of the UC Davis Centrifuge, and established one of the world's really premier geotechnical centrifuge modeling facilities. So he's done a lot of great work there. And then Sumit Kumar just joined us. He's doing field work now in Boston as part of his postdoc. So he's a postdoctoral scholar at UC Berkeley, working with Professor Soga, and earned his PhD at UC Davis just this year in 2022. So congratulations on wrapping that up. And is now working, I guess, in the field on fiber optic cable testing. And I think Sumit did the work that is going to be presented here today. We know how it is. The advisor gets the credit, the student does the work, right?
Exactly.
So the project is published in DesignSafe, project number 2828. And it's from 2 large centrifuge model tests at UC Davis to study liquefaction-induced downdrag. I think rather than read all of this, which many of you probably have already seen, I will just turn it over to Katarina at this point to get started. So I'll stop my share and you can go ahead and start. And as she's got the slides, I'll just mention one thing. If you have any questions, feel free to type them in the Q&A feature at the bottom. There's also a chat, but please use the Q&A if you can remember to do that, and then I'll moderate the questions at the end. So I forgot to say that. Sorry to interrupt you as you were starting, but now it really...
No problem. No problem. And then thank you for the introduction, Scott. It's definitely true. Sumit was supposed to be giving this presentation because he is the one who has been through every single thing that happened in this project, but he's in the field testing, but he's still joining the webinar, and he's open to taking all the hard questions. So anyways, good morning or good afternoon, depending on where everyone is joining us from. First and foremost, we would like to thank the NHERI DesignSafe for recognizing our effort to publish the data from this project that I will be talking about, and of course the opportunity to present about this. I have to admit, this presentation was a little challenging and a little fun to actually a lot of fun to do, because we decided to not show necessarily all the technical details that everyone can find in papers, but utilize the opportunity to share some of our thoughts and motivations behind what we thought was successful publishing. Also, thankfully, DesignSafe thought the same. So this is what we're going to do today. Before doing anything, you get to see me right now, but the team was really Sumit Singha, currently a postdoc at UC Berkeley, the grad student at the time who did all the work. That was his PhD. And then Bruce Cutter, Professor Emeritus, who managed this project together with me and really taught us everything he knows about centrifuge testing. So before anything and sharing the plan for today, I'm going to share some visuals just to get some of our thoughts going. And this is a roadmap of a typical timeline for a centrifuge project. The durations here reflect our experience, but we have found more or less this is the experience of most users. I am excluding the training leading up to anything. So from the experimental design to model prep, then to testing, and then doing the data synthesis and documentation, you can see how short the testing is relative to everything else. And this really plays a role in the importance of everything we do. Then following the data synthesis and documentation, you do the analysis and interpretation leading to publications and hopefully answering the research questions you started out with. Occasionally, there's a connection between the analysis and the experimental design, should you be doing a second or third test. So you use what you learned from the first one to move forward. And then as we go into the data synthesis and documentation, I'm going to emphasize documentation a lot throughout the presentation. First and foremost, we find that we do it for ourselves in our own memory, but also turns out that in the process, you benefit a host of other potential users, whether those are experimentalists coming to the same facility to do not an identical test, but all centrifuge tests do share some common features, so you get to help them a lot. Numerical modelers who are going to use your data, young researchers who just seem to seek to find and learn what centrifuge testing is all about, and also grant writers who want to have some of the details going into centrifuge testing before they put their plans into a proposal. Another way to view this, which becomes important for this presentation, is that we get to see the publishing and evidently the data collection that goes behind it. But really, this is underpinned by a set of other procedures, again, from the design all the way to the preparation setup. And then along the way, you have other considerations like pre-processing, post-processing, the documentation, how you want to do it, the users, and some of the surprises that come along the way to change sometimes your plans. So that goes a lot into how you do instrumentation and how you go about your data. So with that, the outline we put together for the presentation was obviously to go a little bit through the project, because that is necessary, before we discuss the data, discuss a little bit about the design, discuss some of the sources of data. Ultimately, these are the things we published. Then discuss about how this project now looks on DesignSafe, and wrap it up with some thoughts. So the problem we set out to study, funded by Caltrans at the time, was liquefaction-induced downdrag on axially loaded piles. So really quickly going over what this problem is all about. Pile foundations are designed to transfer superstructural loads through skin friction and end bearing resistance, while of course always meeting performance-based criteria in terms of settlements. So occasionally, depending on the soil conditions that surround your pile, the settlement of the soil near the pile interface can drag the pile downwards and generate additional drag load. We know that in the context of clay consolidation, but that can also happen if and when your pile goes through a liquefiable soil layer that ends up liquefying, and then through the reconsolidation process and the associated settlement, the soil also moves downwards and affects the pile. So some of the mechanisms that are taking place, initially starting from a static condition, we see the activation of skin friction, positive looking upwards, together with the bearing resistance, zero excess pore pressures, and a full effective stress profile. So for an extreme scenario, we're becoming a little dramatic here when you have a full liquefaction of your loose sand layer that we have there in the middle. For the amount of time that you have zero excess pore pressures, you lose all your effective stress and your skin friction becomes zero. But then moving on towards the reconsolidation process, as the shaking has ceased and excess pore pressures start dissipating, the soil is regaining its strength. The excess pore pressures are dissipating, as we show there with the isochrones, and the effective stress profile is reestablished. While this happens, of course, the soil is settling, the pile will be settling, and you have some competing mechanisms there that continue until all the pore pressures are dissipated and the equilibrium in the pile has been reestablished. So at the end, we may be looking at a condition like the fourth chart here that I have on this slide, where you have some drag load pointing downwards, and then still you have some positive skin friction pointing upwards. So as we focus on that final condition, and we look at the distributions of settlements and axial loads, we can track the soil settlement and the pile settlement. Commonly, the point where those become equal is the neutral plane, which essentially divides the pile into the part that is subjected to negative drag load, and below it positive skin friction. If we look at the axial load distribution, of course, we start from the head load, which by the time we reach the neutral plane has been increased by this QD, which is the drag load. And then, of course, as we go downwards again and we find that the bearing, the tip resistance, it gets reduced again. Now, all this time, all these mechanisms are very time dependent. There is a sensitivity in that regard. It really depends on what's going to happen first, and whether how the pore pressures are going to dissipate, what the pile is doing in between, and so on and so forth. So ultimately, this is a settlement driven problem, because this also has to do with how the skin frictions are activated. Now, the goal of this project and some of the worries that led Caltrans to support this work was to resolve these mechanisms and find an answer of what is driving the response and what should be considered in applications in practice. So for us, the scope of work was to perform some preliminary numerical analysis. I want to hold that thought, to explore the parametric space and then use them to design the centrifuge model test. We ended up performing 2 large centrifuge model tests. Those are the ones that are curated up in DesignSafe right now. Follow up with some numerical modeling to incorporate the observations, do some validations, see what needs to be advanced, and use those later to develop a simplified method. Now, thinking about the preliminary analysis and what are the centrifuge tests you want to do, you need to start developing a certain, let's call it experimental wish list. And for us and for this presentation, quite simply, first and foremost, you have to ensure that you're going to have a gradual activation of the mechanisms. You want the layers to liquefy. You want to see some action. You want to see the pile settling. You want to see drag loads developing. You don't want to spin up a model and test it and not have anything happening, right? You want to reach failure. At the same time, soil is not an elastic material, not by a stretch. So all this needs to happen gradually so that you can observe the phenomena. You need to measure the settlements of the soil and the pile. That is key. You need to measure the structural response of the pile and the loads along its length. And you want to track the excess pore pressure distributions in time so that you can see how those coexist, I guess, with the settlements experienced. So going into the centrifuge model test designs, I will not assume that everyone in the audience has performed centrifuge model testing. So quickly, a slide on this. This is a slightly older picture of our 9-meter radius centrifuge, but the essence has not changed. You have this this is what we call the arm, and this is the bucket. So essentially what happens is as the arm starts spinning around this vertical axis here, the bucket starts spinning up. So essentially this is where you put your containers with the soil structure systems that you want to study. In a reduced scale model, you just have an n factor that scales basically all the properties. But what happens in centrifuge model testing, the centrifugal acceleration as you spin the model around is essentially compensating for gravity. And for systems that have soils where we know that everything is so dependent on gravity and the stresses in the soil, this becomes particularly useful. So in this part of the slide here, I'm showing this model essentially rotated, similar to what would have happened here in the bucket. We have a whole series of established scaling laws. N that you see here is the centrifugal acceleration. It's scaling linearly properties like length and accelerations and densities. And depending, of course, on other properties, the scaling laws may be a little different. So the general model details, and again, I want to focus on some of the features that led to data and not so much on the mechanics that we ended up learning about. The preliminary numerical investigations, we did explore the parameter space in order to determine some of the critical scenarios we wanted to study. We wanted to have models that would emphasize some of the key things that we found from a literature review would matter. So apart from helping design the centrifuge test, preliminary numerical investigations can really help you establish the type of data you will need. And they also serve as a rehearsal for post-processing. So they help you prepare all of your codes, both to use after you're done testing, but also while you test. And I will talk about that in a little bit. Quickly, now we have two cross sections. The left one is centrifuge model test SKS02, and the right one is SKS03. Their differences right off the bat is that SKS02 had 2 piles and SKS03 had 3 piles. The former one had a more simple profile, a very thick loose sand layer. We wanted to start simple before making our lives more complicated. And then for the second test, we had a slightly more layered soil profile. Now here I'm showing the instrumentation. It's going to come in the next slide as well. But we used obviously the 9-meter radius centrifuge at UC Davis, a flexible shear beam container, essentially a laminar box. We operated the centrifuge at 40 G. We scaled, our scaling for water was essentially a pore fluid that had 25 times the viscosity of water. And we used a series of scaled Santa Cruz earthquake motions, which goes back into this gradually imposing our demands. And on the bottom, I have the properties of the pile. These were made of aluminum, but they were designed to represent more realistic field conditions as provided by Caltrans. This is a full view of SKS 03. Now here, anything that is a circle, either blue or yellow, is a pore pressure transducer measuring pore pressures. The green arrows or triangles are accelerometers of different types. And then the red lines that are shown on the piles are full bridge strain gauges that we use to instrument the piles internally, not externally. And I'm going to show some pictures on that later. You can see some of the dimensions. These are all in prototype scale, and some of the layering information here. Now, some of the considerations that went into these centrifuge tests. First and foremost, I said that before, every centrifuge test is unique. So you may or may not find extensive documentation. More often than not, you will not find such an extensive documentation on every single aspect that you need. So it is really important to be aware of that, but also try to pay that forward and develop documentation for future users. You need to know the facility equipment, what is available, what the capacities are, and what the limitations limitations are. For example, the containers. You need to appreciate the fact that once you're done building your model, you have no idea what is happening inside. So you need to keep that in mind as you design your instrumentation, and in particular, consider characterizing it before and after each event, such that if anything goes wrong, you at least know exactly when and how and what the state of the model was. Money and overhead is always a consideration, so that needs to come into play. The timeline, sometimes some of the things that you want to machine or customize or purchase, they have significantly long lead times. So we have found that throughout the pandemic, this has become even worse. So that's important to keep in mind. And really going back to one of my first slides, this is a one-off opportunity, and your soil is not elastic, so you really want to have some redundancy in what you do. You may have sensors failing, you may have other equipment failing, so particularly for the measurements that are really key to you studying the mechanisms, you need to make sure that you're covered. Okay. Now going into some of the decisions, we had the considerations, now we made some decisions. We made the decision to have preliminary numerical analysis. We made decisions on all the things that went into the box, the properties of the container, sorry, not the box, their properties, how those would look like, the layering, the dimensions, instrumentations, calibrations, what the testing sequence would be, anything from applying the earthquake motions and to any CPT or any pilot test that we wanted to do. Anything on pre-processing, co-processing, and what I mean by that is processing the data as you record them while you're on the arm and testing. Trevor Carey gave a presentation on that, I think a year ago. So if you apply a certain shake, you need to see how things are going and adjust. Some of the things that you do, either reduce the demand or increase the demand, or before you come in the next day, you might want to change something. We ended up doing that. We ended up changing the head load for one of our piles during the second day of testing. So that was particularly important. And you need to also prepare yourself for some significant post-processing. And of course, the schedule and contingency plan for both preparing and testing on the arm. In our project, we found, and that's also quite globally true, that everything that you desire to do experimentally and actually decide to do can bring new challenges. But if you use them as opportunities for advancements in testing, that can be actually quite rewarding and beneficial for the project, and we have found for the community overall. Some of the challenges and opportunities in our tests. As I mentioned before, we wanted to have a really good grasp of the axial load distribution in the piles, which is why we instrumented them internally. We did not want to compromise their external surface because that was important for the whole activation of drag load. This is something that other projects have done in the past, but not quite in the resolution that we did. We ended up installing 9 full bridge strain gauges internally. We wanted to have measurements of settlements both in space and in time. And the more gritty you get with the number of measurements you want to get, the more crowded your specimen can become. So we ended up developing contactless sensing methods. We wanted to have a good resolution of the pore pressure migration, but pore pressure transducers can get really expensive. So we also developed some of the low cost PPT sensors I'll show in a few slides from now. And this is not something I'm going to show slides on, but we had to consolidate our specimen, particularly for its top clay crust in the prep room, which meant we couldn't consolidate on the arm, which then meant that we would have to first consolidate and then transport the whole container over to the rotunda at the Centrifuge facility. So we wanted to make sure that the liquefiable layers would not get densified throughout the process. So we had to perform that under vacuum conditions. So some of the sources of data for the soils, for the soil and the piles, just pictures of them ranging from accelerometers to pore pressure transducers cameras, two different types that we used. Lasers, we use them in combination with the cameras to obtain settlement measurements, a 6 millimeter CPT to characterize the profiles, and a 10 millimeter probe for performing a pi load test in our models. For the piles, I'm showing here some pictures. This is a schematic of how the pile looked like. This is the pile in Sumit's hand so that you can get a sense of how big it was, then how it looked in model scale inside the centrifuge model. That is during the dissection, excavation, essentially after shaking, after getting off the arm. I have some pictures of that later. And these are the types of measurements that these provided to us. So they gave us axial load distributions, and these are isochrones at different times throughout shaking. What you see up here in the schematic and here in 3D is the pile mass that we used to induce the head load, and that was modular so that we could test different lengths of pile, but also keep that as low as possible, closer to the soil profile, so that we would avoid any bending, because we wanted to isolate bending actions from axial actions. Now the three piles here, you can see the masses here and how they look like, the cables coming out. These are all for the strain gauges, and a 3D view of the instrumentation as it looked like on the arm with the accelerometers. Here horizontal one, here a MEMS one, and then a vertical one on the pile body. For the settlement measurements, we actually had two methods. So first, I will talk about the issues that we had, or that anyone would have, with standard LVDTs, LPs, and LDTs. Here, a schematic of how this typically looks like, where you place the instrument on a support beam. It has to be supported by that, and then it's tracking the target as it's placed on the soil. Now, of course, the soil will settle or move and tilt, so that will affect the point of touch, but also that is imposing some demands on the support beam. And most importantly, here I have a plan view. The support beams will block your view off the model, and things can become quite crowded as you install more and more of these types of instruments. So we did have some of these, but we also, in order to get the resolution that we wanted for the surface of the model, we followed two methods, and overall that became some reports and then publications on the development and implementation of contactless displacement sensing methods. The one of them was 3D stereophotogrammetry, and the second one, the combination of one camera with a line laser. So first, I will talk about the 3D stereophotogrammetry. And the concept is pretty simple. If you combined views from two or more cameras, you can post-process them to obtain and fully characterize the 3D position of a point. This comes with Photron high-speed cameras together with the TEMA software, as it's called. And it has been used for other applications, as I'm showing here on the right part of the slide. Now, in our test, we used 4 Photron cameras. They're shown here on the right, C1 to C4. Here I'm showing their properties. They have to have a really great resolution, shutter speed properties, and frame rates, which makes them really expensive. But also quite beneficial, as I will show in a bit. These are two views of pile 1 and 2, and 2 and 3. So you have to ensure that the cameras are going to overlap a little bit in what they've used, so that you can use them later in the post-processing. This was the first combined use of high-speed cameras and subsequent image analysis to measure the 3D movements in the centrifuge test. So it worked quite well. Now, of course, you make one decision, and there's cascading consequences following it. And in our case, that was the design of this beam that you see here. In plan view, you will see it here and on the side right here. So we had to design a camera beam and holder mechanism that would be staying intact and protect the cameras, but also ensure that it's modular enough so that it can be reused in other tests and other configurations for future users. So you can see here a zoomed in version of how the cameras look like in the AutoCAD drawings. And here a side view of the model. Now, of course, those have to be used in combination with some target markers here showing the soil markers that we place. You can see them here, essentially placed on the soil. Some markers here on the side for the container. Some markers also on the mass of the piles. You can see them here, 1, 2, 3, and then also we used grid paper for the mass so that we can have the cameras can have something to look at. 3 types of results that we got from it, and here comes a little bit the issue of having redundancy. You really don't want to do something so new, as novel as it is and as fascinating. You cannot go into the test thinking that is always going to work. So we were a little conservative there. Here, and there's actually a video playing. The plot here shows the movement of pile 2 and the sensor on the soil, S33. So you can see what happens during shaking and during reconsolidation. So we are able to track that. We also, with all the distributed markers on the soil, we were able to get contours of the final settlement in the model. Those became really important for some of the analysis that we did later. And here on this plot, I'm showing acceleration obtained from the 3D stereophotogrammetry, actually the post-processing of the cameras, but also from the accelerometer. So this is a nice proof that the method works quite satisfactorily. The other method using the laser line and the cameras essentially also quite simple. You use a laser line to provide a target for you, and then we use GoPros to record the apparent horizontal movement of a projected laser. These images here are essentially overlaid before and after view. So you can see here the laser line moving with simple geometrical calculations. You can see this is the initial point and this is the final one. So you're looking to get the delta U and delta V, how much laterally it has moved, how much vertically it has moved. And it really does have the benefit of being really cheap. The lasers were something like $30. GoPros are quite inexpensive compared to everything else right now. You can track multiple targets, and the accuracy is comparable to DIC methods. Some of the results that we got from this method as well, compared to 3D stereophotogrammetry. I'm showing again the same video as before, and you can also see that the comparison is quite well. So this is for settlement, and then showing the settlement across this strip, this blue strip on the profile, on the surface of the model. We can track how the surface moved, and we're comparing it here with some of the local targets that we had. Last, from our instrumentation, we had a very dense network of pore pressure transducer arrays. We could not afford to do that with some of the more expensive pieces. So the blue circles that I showed before, those are the Keller PPTs. Those were $1,000 a piece. So we couldn't use so many of them, but we really wanted to track pore pressure patterns across the model. So we found these really, really cheap pore pressure transducers. They were not waterproof. So we added a pore stone at the tip, and we epoxied it with this adhesive here so that it would become waterproof, and they worked quite well. They are the yellow dots that you see here in this cross section. And here what I'm showing is these 3 PPTs here at the tip, close to the tip of the piles. So the top plot shows excess pore pressure, time history during shaking, and then the bottom plot shows reconsolidation. So basically, this plot here is scrunched somewhere here in the really in the beginning of the horizontal time scale. Now the red line that is hidden in the back is the response of the free field right here at the same elevation of these PPTs. And then the gray lines are those of the cheap PPTs, let's call them like that, close to the piles. Now one can look at different things that may be observed here. You can see different dilation spikes. You can see that the field doesn't have much of dilation spikes, really small actually, and depending on the load of the pile and how much it was mobilized, leading to different responses in the
All right, can everybody hear me? I think Katarina has frozen.
Yeah, I can hear you.
You're there, Bruce?
Yeah.
Okay. Do you want to pick? Oh, her slides went away now, so there's nothing to talk about. I don't know if you have a copy of the slides, or do you have them, Sumit?
I don't have them handy.
Yeah,
no.
I have them in the box. It is in the box.
I could download them and do that, but it'll take me a minute.
Okay.
And I don't know if I mean, I haven't prepared to present this presentation.
Okay.
Sumit and Katarina did it, so I could.
Where did you lose me?
She's back.
I'm back.
Yeah, it was about 35 minutes ago. No, just
No.
just froze on the slide showing the pore pressure transducers. So go back right here. It was on this slide.
Yeah, right.
Okay. Did you hear me talking about the data?
Yeah.
Yep.
You said we heard most of it.
Okay.
It was only a minute,
okay.
So you're good.
Good. Okay. Okay. So anyway, we found that the pore pressure transducer worked quite well. The cheap ones as well. I mean, the expensive ones, they better. Okay. Breath. Model dissection. Okay. So this does not count. It does count as data, right? It's not the conventional data that we find through instrumentation, but it does help a lot in understanding and supplementing everything else that we measure. So this is a view that we took from a Handycam scanner, quite cool piece of equipment, and this is an actual picture of the model. So what you do in dissection is you essentially do vertical cuts of the model, and then you progress backwards to just see methodically what your model looks like inside. So it's essentially a little bit of a forensic investigation. So you're looking to see how things displaced, how the pile looks like after you installed it, where the sensors ended up being. You think you place them somewhere, but sometimes things shift around. They can also help you see where everything settled. So the more methodically you do, the more you can later on also help. They also help you correct your data, should that be the case. So these are the excavation fronts as you're approaching the piles, almost seeing the piles, pile 1, 2, and 3 for SKS or 3. So you can see the PPTs and how close they were to the pile tip. You can also see how much the pile has displaced. So these all go into our records and help us cross-validate what we measure from externally. Other things you can see is how much the soil settled with a nice vertical cut. You can see that the different layers and their colors and see their thicknesses. They see where everything is. and again, use that later. You can also find cool features like sand boils and how they crack through the crust, or how they look like from the top, or see if any bulbs developed as you were installing the pile. You can also see and in our case, we used colored sand, how much it displaced as we installed the pile. And if you want, use that later to see how much friction you activated during the installation. And this is a piece here from the crust. So you can see that this is actually a leftover of how it was placed in this thick paste that this picture shows right here at the bottom left. Sensors may relocate as you do the placement or later on in the process. So it's nice to go back and see where they are. In some cases, and that's something that we actually had done back in LEAP, that my role there was just as a numerical person. Sometimes you can find, the location of a pore pressure transducer by just seeing what is the maximum excess pore pressure it reached, should that be full liquefaction. If not, then things can become a little challenging. Anyway, so these were all the sources of data, and I tried to supplement them with some of the thoughts and the considerations that went to them. Now on to data publishing, and some of the DesignSafe webinars I've attended, the motto is, data uploading is not data publishing. And now that's actually really, really true. So this is PRJ 2828, the home of all the data for our 2 tests. So this is the figure you will see as you go into it. And these are the 2 depots for the 2 tests. So each one has a DOI, and the data is right underneath it. So as you open one of them, you'll find the description and some of the metrics and a summary and so on and so forth. And the meat of it comes once you press the button to see what lies underneath. So it starts from the report. I will open it up in a little bit so that you see what's underneath. Model configuration, and then the sensor information. Now, the sensors are organized by event. And this is every single thing that happened throughout testing. SWM stands for step wave, CPT cone penetration test, and that's what we ended up doing. First, we did the step wave motion to essentially see that everything is working. Then we did a cone penetration test in flight to get a reading of our profile with CPT. Then we did a pile test. Then we applied the first earthquake motion, and so on and so forth. So I'm going to now open up this green area here so that we see what somebody can find in there. And you can see that there is the data report. There's the configuration of the model, both in cross-section and plan view, so that somebody can always know where everything is. And then the Excel sheet with the sensors. Now, I personally find that for somebody not familiar with the test, they should always start from the top folder. So let's see what is here. So first and foremost, we have our a README file for how the files are organized. So Sumit went in there and described everything that is up there. So what I'm doing right now is in a 2-page PDF. There's also a README file on how you read slow and fast data from the Centrifuge. Not everyone knows how to do that. So there's instructions there, and they're accompanied by Python code that Sumit is publicly sharing through his GitHub profile, just to make the lives of people easy. The data report is right underneath that. I will talk about that in a little bit. A folder that contains all the details on image processing. The data acquisition database has all the raw sensor data for all the events, but also those exist in a process form and prototype scale now in the folder called processed data. We have also put picture snapshots from the events from the different cameras and all the recorded videos from both the Axis and the high-speed photon cameras. Some of those files are a little large, but no problem there. And the laser scan folder contains 3D surface. Those are STL files after the experiment was finished. And just so that I can show what one of these events contains, just randomly picked earthquake motion 4. So in there you can find bin files. Those are raw data from the centrifuge, some pictures, JPEGs, just to see the before condition and the after condition from the earthquake motion, process data in Excel format, and some of the videos in these folders here. So we have included everything in all possible formats. And that's all thanks to Sumit. I have to emphasize that. Okay, so last but not least, the report, and this report is extensive, and it's extensive first and foremost for us, so that we know exactly what went in. It really helps to go back. Memories can be fickle sometimes, so there's no better way than just to put everything in a report. This is the outline we follow. We have found that it works for us, but we think it's a nice blueprint for other centrifuge tests to follow for those who are looking for something to follow and that don't come with their own experiences and opinions. It also includes a large appendix with everything plotted. So all the data you will find on DesignSafe are also plotted inside the report. So some closing thoughts for this presentation. 2 questions that we thought would be useful to answer for this presentation. How do you decide what data to collect? And that has to do with, first and foremost, identifying the mechanisms of interest and designing a test that emphasizes those. This is what Dan Wilson, the associate director of the Centrifuge, likes to always say and emphasize to new users. And once you decide that, you have to place enough sensors to get the data that will elucidate the mechanisms. And you need to have some redundancy on those. You need to know beforehand what you will do with the data. Initially, guilty as charged. I thought we instrument, we put it up there, we spin, and then we work with the data. No, you need to have a plan so that everything is meaningful and thoughtful. The state of any soil model is very much history independent, and you don't know what happens inside of it. So that needs to be always considered. And then again, pre-processing, co-processing, and post-processing, all of those are equally important. Now, how can you achieve maximum impact? Make your data count. I don't know if Ellen is online. Obviously, making your data readily available through open access platforms like DesignSafe, which has, again, provided a great home for our work, is definitely one step. However, in the process, we need to recognize that the curation and publishing, it's not externally vetted. So it's really up to you to make sure that your data is usable. It's one thing to appreciate and obtain a DOI, and it's another thing to actually get that DOI to be used and referenced by others. So, with great freedom comes great responsibility in this case. So, and the other thing is that journals have greatly now started asking for data availability statements. But again, it's one thing to say your data is available, and it's another thing to have somebody spend countless hours trying to figure out what to do with your data and how your data is organized. So uploading is not enough. The detailed documentation is really necessary. It needs to be understandable. It needs to be easily readable. And in our case, we put all the process in just one document. Archiving the data in a format which is easily read, understood, and manipulated, like text files and Excel spreadsheets, is always preferable. And then, of course, for non-trivial data files like bin files from the Centrifuge, providing scripts to convert them to something easier, I guess, is always preferable. And since you're at it, why not provide the process data too, as a numerical modeler, slightly converted to an experimentalist. I will never claim that I'm a full experimentalist. Increasing the utility through that regard is amazing. So as a numerical modeler, I really appreciate that. And the last thing is that embrace the challenges of the models for us, particularly the contactless methods of tracking settlements, where a slight tangent in the test, but really rewarding. And now we have new methods and equipment at the Centrifuge available for others. And Jack Montgomery out of Auburn University ran a test this summer with 3 REUs and his grad student from Auburn, Alani, and they used the high-speed cameras and the TEMA software and Sumit's report, and it worked great. So that was really nice. And ultimately, the best audience sometimes is ourselves. So we need to start by keeping ourselves happy and our records. You don't need to worry now where your data is and what you did. Go through handwritten notes. Now everything is in a report. It really helps in data interpretation and helps others in their own tests. So with that, I will share 2 groups of publications and references that came from this work. The top 3 rows, the yellow colored ones, are reports and the data set together with the DesignSafe repo, and then outcomes and actually technical work that we did facilitated by the data is in the gray references in the bottom. With that, I hope I'm on time. Yeah, I'm on time. And me and now Bruce and Sumit will take any questions you have. Thank you very much.
All right, great. Thanks, Katerina. I'll clap for you. The attendees are all clapping too. You just can't hear them through the webinar format.
Okay.
We do have some good questions. I see that Sumit answered one of them about how the piles were installed. So, you know, I don't think everybody can see those questions though. So maybe I'll just read that the piles were installed by pushing them into the soil using a heavy mass. And Sumit did provide a link there where the documentation can be found. So the next one, Amalesh Jana says, you recognize that your sensor has moved after an event from the cross section from its initial position. If you do multiple events, how do you know the original location of the sensor at the beginning of that event? And does that change your final data analysis? And you can feel free to delegate the question to Sumit or Bruce too.
I'll take the first tab, and then I'm sure they will chime in if I mess something up. So first of all, Amalesh, great question. You don't know what's going to happen in between the different events. You know the beginning and the end, or you at least know where you place your sensor. On certain occasions, you can get the final measurement and just back calculate. And then it also depends on what that sensor is. It's different to be an accelerometer or a pore pressure transducer. You can only know so much. Sumit, Bruce, anything?
Yeah, for pore
that you guys do?
Yeah, for pore pressure transducers, actually you can find out how much it has moved, because you can always measure hydrostatic pressure. So with that, you can know what is the location after each subsequent event. For accelerometers, it is difficult to do that. And that's why it's important to do model excavation at the end. So in case things has moved during the whole process, which it might be because the layers are settling down, so it will move. So it's always useful to do the post excavation of the experiment of the model and find out where are the final position of the sensors. And during the installation, you know what were the initial position, and then you can use that information to analyze your results.
There's also a follow-up question from Amalesh on the same thing that was just added. If the PPT moves laterally.
Right.
If it moves laterally, then hydrostatic pressure is not going to help you much.
But
I
the
think.
vertical position is usually more
The
important.
vertical.
Is more important anyway for knowing the results too. Small lateral movement for the PPT is not usually so significant unless it's the one right next to the pile or something like that. Yeah, but you can't. We don't have a way to know that.
All right, thanks. So Amalesh also asked about group interaction. So in the model, you did single piles, but piles are often, or drill shafts are often installed in groups. So are there plans to do a group test, or how could these results be translated to group analysis?
Bruce, you want to take that?
Well, that's an
Or
important
Sumit?
question, and I guess the answer is we have just been thinking about the single pile up to now. That's obviously it would make a difference because it's the relative movement between the pile and the soil that controls the downdrag. And so that would change. You'd have more group action that would drag more soil down. So yeah, it'd be a lot more complicated. Interesting though.
Yeah.
And the soil in between the piles would behave very differently. You may have arching effects,
Right.
the pore pressure patterns would be different. So that's we don't have any plans yet, but who knows?
All right, great. And so how did you manage to create the relative densities for the different layers? The automatic or manual?
I assume this is a question on sample preparation and pluviation?
Probably,
Yeah.
just
Yeah.
a question about
Okay.
pluviation.
Sumit, you want to answer that?
Sure. So yeah, the model was prepared manually, or the soil was placed manually. We prepared the relative densities by showering the sand from a particular height, and by controlling its volume, how much it goes down. So that was the process behind placing the soil with a particular relative density. And of course, we did a calibration first to find out what relative density we would get and how to control the falling height and the volume. And then we prepared our model accordingly.
All right, great. Thanks, Sumi. Yeah, the next question is an interesting one that I was wondering about too. If you have standing water on top of the model, like in the LEAP project, would the cameras still work well? And I noticed you did have a little bit of standing water on your models. So in addition to the cameras, like what about the laser? Does the laser reflect off the surface of the water instead of going down to the soil?
Yeah, in fact, sorry. Bruce, go ahead.
Okay,
Bruce, you want to talk about Nick?
I guess I'll answer. If the water layer isn't very thick, then you can sometimes see through it. If the water's thicker, sometimes you see two laser lines, and you can use that information to detect you get the refraction line and the reflection line, and so then you could tell the depth of the water. But if it's murky water, then yeah, you're messed up. But most of the time in our test, the markers stuck up above the water, and so we could at least see with the photogrammetry, we could see those markers, and the laser lines also hit the pile caps, and so they were useful there. And in LEAP, we use cameras too, and if there's a lot of water, you can make a camera that goes underwater and looks at markers underneath. But yeah, if you've got waves on the surface and reflections, especially light reflections on that water surface, were bothersome when you're trying to do the image analysis. But yeah, we tried to have a thin layer of water so that wasn't too much of an issue. Does that answer the question?
A little challenging.
Mm-hmm.
It became a little challenging during testing as you had liquefaction, and the water would come up in the top, but it didn't compromise the measurements. The other thing that also wouldn't work, but it has been considered in the facility in the past, has been to use one of those handycam scanners, at least for before and after testing. You cannot use that in flight, but that doesn't work if you have water. If you have a dry specimen though, or a specimen that is saturated underneath the surface, those can work for before and after at a minimum.
Great. So we're getting close to time. I know people may need to start filtering out, but there are some good questions here. And if you can stick around, I'd like to hear the answers. Is that okay if we go a little bit long? Okay.
Yeah.
So there's a question about the saturated clay layer. Did you use a high viscosity fluid for the clay?
To me,
No.
Yeah.
Yeah, we did not use the high viscosity fluid because that will take forever. We just used water for saturating the clay layer.
Right, and that clay is probably still undrained even with water, right?
Yeah, it would still be undrained. So one of the important aspect is to make sure the mechanism that will happen in the test. So even by using water, the permeability is so low that it will still remain undrained during the test.
Right.
That's why we did not need to use high viscosity.
Great. Then another one, 2 questions. So did you consider lateral movement of the soil along with settlement of the liquefied layer, and did it have an effect? And then a specific question on the settlement contours. Why did the soil around pile 3 settle more than around pile 1?
So for the question number 1 is easy. We did not consider the lateral movement of the soil. So we
we
don't
did
know
measure
anything
it
that-
though. There was some lateral
Yeah,
movement.
but we did not. A little bit.
With the cameras, you could measure.
Yeah, but we did not account it in the analysis.
Right.
Yeah, okay.
Yeah.
And then what was the other one?
Second
Oh,
one was,
settlement.
why did the soil around pile 3 settle more
Yeah.
than soil around pile 1?
So the soil at, I think one of the reason could be pile 3 was the heaviest pile, which means it had a bigger mass, and all the 3 piles were at the same depth, embedded at the same depth. And pile 3, because of the heavy mass, plunged in the ground during the testing. So maybe that led to some extra settlement that you observed just near the pile.
But when
The
the ground,
forest level.
there's also the issue of when the ground liquefies, it re-levels itself. And so, it's not perfectly level to begin with. And sometimes the
Yeah.
centrifuge bucket angle is got a little friction in it. So the bucket is actually tilted by about 1 degree or something like that, a very gentle slope. And so then there is also, in addition to what Sumit described, a tendency for the ground to shift a little bit due to that very gentle slope. And I think that explains part of that. And also it forms the curve. It tends to form the curve associated with the radius of the centrifuge. So those things make the soil settlement non-uniform, and it makes it particularly important to measure settlement all over the sample and without assuming that it's uniform.
Correct.
All right, great. So let's do one more question, and then I'll show the little QR code again for the survey. So from Brad Wem, thanks, Katerina. I want to ask about where you decided to attach the cameras. It looks like the mounting bracket is off of the shaking table. And did you consider having them attached to the shake table? How was the decision reached about where to put those?
Let me pull the
Yeah.
sketch here.
So
It
the
is on
camera,
the
should I answer?
Yeah. Go ahead.
Yeah.
I'm gonna pull it
So
up.
the placement of the cameras was such that we cover the whole model. So we used 4 sets of cameras, and you need one pair of cameras to get a 3D movement. So we made sure that through those 4 cameras or each individual pairs, we are able to see the whole part of the model. So overall, we used 2 cameras to see the north part of the model and 2 cameras to see the south part of the model. And so basically we covered the whole model, and that described the placement of the cameras. The other things also to consider while placing the cameras is how close you can look at the model. The further close you are, your view will decrease, but you get more resolution, right? And as you go backward, you get more view, but smaller resolution. So we did some analysis to find out what is the distance away and what is the view angle that we get good resolution at the same time, good length of data or good view of the model.
And are displacements always relative to 2 different things that are in the image? So the movement of the camera body itself doesn't really matter, right? It's always relative pixels within the image. Is that right?
Yeah, so yeah, so the whole camera beam and everything was not placed on the shaker, it was outside. So we were measuring absolute movement. And often we are interested in measuring relative movements with the container, right, as the container is shaking. So during the analysis, we actually when we are using the cameras, we also place some markers on the container so that we can get container movement. And then we subtracted the absolute movement of the targets with the container movement to get the relative movement.
Right. Okay, great. Thank you. So I think we should wrap up here for the sake of time. Let me, oh, Katarina, would you mind stopping your share? And
Yes. Yeah.
Oh, I thought you said, yes, you mind. You said, yes, you will stop.
Yes, I'm such a.
Okay, so let me share mine if I can.
So shocked by my internet.
There we go. So just a reminder, the video of the webinar will be up on our training archive, which you can access through the DesignSafe Learning Center. It has a link to our YouTube channel where you can go and watch this or forward it to other people. And then here's the QR code. So we appreciate your feedback. You know, go ahead and take a moment to scan that. And it's a pretty quick and painless survey. We really do look at the results and use them as part of our annual report and so forth. And so I want to thank again, Katarina and Bruce and Sumit. Thanks for being here. Congratulations again on your Dataset Award. And thanks for putting the effort into making such a well curated and valuable data set. And so thanks everybody for coming. And I think that I will go ahead and stop my share and we can end it there.
Thank you.
Thank you, Scott.
Thank you.
Been our pleasure. We really appreciate it.
Oh, Sumit. Thanks, Sumit, for